of CosmoQuest Astro Office Hours. I am your host, Dr. Matthew Richardson, and let's have some fun with science. But of course, it's a business first, so I need to go ahead and go to Twitch and make sure that I'm actually streaming live. So please bear with me while I do that. So we're going to go ahead and open up a Chrome web browser and navigate over to Twitch. And make sure that everything's on the up and up. All right. Some days this goes really well. I just pop on the Twitch and everything's just right there and it's all set up perfectly. And yes, things appear to be just fine. Let's reboot the page because I need to be able to pop out my chat. See if that fixes things. Nope. All right, let's close the web browser. This always seems to fix the problem. Reboot Chrome. Go back to Twitch. All right. And all right, there we go. So now I'm able to pop out my chat and see who's all here. So I'm not sure if my list is completely up to date right now, but hello Susie, hello Larry of G Cloud, hello Michael T Mayer, and hello Peter Q 1978. Welcome to today's stream, guys. Hey, so that's weird. So I see you're the first person that has made a comment, at least from my perspective, Guido, and for some good reason, it doesn't show your name in my list. But hi, Guido. Welcome. All right, guys. So we're going to be picking up where we left off in last Wednesday's or this past Wednesday's stream, talking about stellar sizes. More specifically, the So no, we're not going to be doing Eddington limit violations today. We're going to be talking about sizes of stars in clusters, or in a single cluster. How can you be able to compare their sizes? And long story short, you're able to compare their sizes based off of how bright they are. So yeah, that is weird. I agree with you, Guido. That's very weird. Because I'm unable to actually see like who's physically here. So if more people join, I'm not seeing their names in the list, making it difficult for me to say hi to them unless like they say something. So yeah, we're gonna pick up where we left off. And I'm gonna go ahead and just jump directly into this problem because I have a new problem for today, which I hope is fun. At least when I first saw the question in my physics book, it looked pretty fun to me. Alright, so to kind of go back over what we were discussing last Wednesday, the objective for today is to estimate the relative sizes of two stars that are in a cluster, and the only information that we're given about these stars is that their spectra, at least for star 1, its spectra peaks at a wavelength of 500 nanometers, and as for star 2, its spectra peaks at a wavelength of 700 nanometers. And the ratio of their apparent brightnesses is 0.091. And so I started off by stating that to solve this problem, we're going to end up using Stefan Boltzmann's law, which basically relates the intrinsic luminosity of some source of light, in this case, some source of light, to its physical size and its temperature. And so that's the equation there for Stefan Boltzmann's law. Now, of course, I've modified that definition specifically for stars. You can go elsewhere to find out what the more precise definition for Stefan Boltzmann's law is. So basically, the luminosity of a star is equal to its surface area, which is 4 pi r squared, or not its surface area, but no, it's surface area, 4 pi r squared, times sigma t to the 4th power. All right. And so upon comparing the two stars and using Stefan Boltzmann's law, we can derive the following, which relates their physical sizes to the ratio of their luminosities and the ratio of their temperatures in the following manner. All right. Now this problem really doesn't take much time. It just requires setting up a few relationships with the information that we're given. So let's go ahead, because now since we know that what we're looking for, which is the ratio of R1 to R2, let's go ahead and determine these other two ratios. That is the ratios of their luminosities and the ratios of their temperature, or the ratio of their temperature, excuse me. All right. So going to my text window, let's make it a little bit bigger so you guys can actually see what I'm typing here. There we go. We're going to go ahead and solve for the luminosity ratio. So no indent. Solve for luminosity ratio. And so I'm going to go ahead and copy and paste the statements for, the statements for being able to make a math array. And so we end up getting a diffraction. Well, first off, we're given the brightness, actually. So let's define what the apparent brightness is. And I believe I showed this on the web during my last stream. But the brightness of the objects, so I'll put brightness B, is equal to, and I have to remember this, it's the luminosity of the object, L, times its surface area. Or, not times its surface area, let me correct that. It's the luminosity of the source times the surface area of the sphere that the light is passing through. It's a flux. So in this case, I'm going to put 4 pi r squared, but the r in this case isn't really the actual radius of the object. It's the radius of the sphere in which the light's passing through. So 4 pi, and let's put lowercase r actually, r squared, so it can't be confused with the r above. Even though for all essential purposes they can mean the same thing. So solve for luminosity ratio, and let's make sure that we indicate that this is the brightness. Brightness function. All right. Scroll down. So there's our brightness function. So again, if we want to be able to, let's say for example, compare the brightnesses of two stars, we can simply just divide this equation by itself. And what we'd end up getting is the following relationship. So comparing brightnesses. Let's modify that to say apparent brightness function. Dash no indent. Comparing brightness yields. And I'm just going to put the answer for this. Assuming R to be the same value in making this comparison, we can end up getting the fact that fraction that B1, or the brightness of one object, relative to the brightness of another object, B2, their ratio will end up yielding the ratio of their intrinsic brightnesses. So L1 over L2. And we have that. And so if you remember earlier, we were actually given, and I'm going to scroll up for a temporary second here. We were actually given the ratio of their brightnesses in the problem. It states that the ratio of their apparent brightness, that is B1 divided by B2, is equal to 0.091. So we actually now know the ratio of their intrinsic luminosities to be this value. And so I'm going to put down here that this is equal to 0.091. I'll go ahead and typeset that. And we can scroll back down, and there we have it. So we have the ratio of our luminosities. The only thing we have to worry about now, of course, is determining, well, what are the temperatures of these objects? Well, there's this little law known as Wien's law. So no indent. Wien's law. And Wien's law allows us, in the case if you have a spectrum that exhibits the properties of a black body, Wien's law allows us to be able to relate the peak wavelength, or the wavelength at which the source has its most energy in, or the peak wavelength, because wavelength and energy are synonymous with one another. We can relate that peak wavelength to the temperature of the body, or to the source, or the star in this case. And so, what we end up getting from this law, and I'll quickly write out the law here, align star, and align star. We end up seeing that Wien's law states that that the max wavelength, so lambda underscore, and I'll put max because it has to be the maximum wavelength of the spectrum, times the temperature of the body, T, is going to be equal to some constant. So I'll go ahead and oops, I did something wrong here. So what did I do wrong here? Lambda, or maybe it'll tell me the underscore. It doesn't like the, I'm missing a D. Lambda. It's my fault. There we go. It's equal to a constant. So we're not even going to worry about what the constant is in this situation. We want to be able to set up a relationship between the wavelength and the temperature of two different bodies. And I think I remember stating this in my last stream, that if we take ratios, this makes life so much easier on us. So we're actually going to do the exact same thing we did with the brightness function. And I'm going to take a quick break to look at comments. Hey NJ Valet, welcome to today's stream. Am I part of the Twitch EDU community? I am not officially a part of any Twitch community, but it sounds cool though. If I get the chance, I'll go ahead and check it out. So thanks, Guido, for covering that for me. Um, but yeah, I'm definitely going to go ahead and talk to my boss Pamela about this. There you. Oh, you guys are talking about is it food? I see recipes, but man, you guys are getting me hungry. I keep remembering that like this time for you guys is like dinner time. It's lunchtime for me, and I typically eat lunch after the stream. All right, let's go ahead and continue though. So I'm going to do the exact same thing. I'm going to go ahead and divide this equation by itself, and I'm going to put little subscripts to indicate which object I'm talking about. So to make this a little bit easier on myself, I'm going to go ahead and copy and paste. So comparing temperatures, let's put it that way, comparing temperatures, yields, and of course we're doing this through Wien's law. We're going to end up getting lambda max for 1. Oops. So let's see if this will work. I think I could put another underscript 1. And of course, I'm going to divide this by lambda max 2, which corresponds, of course, to the maximum wavelength. Not the maximum wavelength, but the peak of the spectrum that's produced by these two stars, where that peak occurs at some lambda value, must be equal to, and of course I'm modifying this so that I can automatically just be able to get directly to the result. So lambda and temperature are inversely proportional to related to one another. So on the right hand side of the equation, I'll get temperatures, of course, and of course the constant divides out. I'll get, I think it's T2 over T1 on the right hand side. Let's go ahead and typeset that. Okay, it's not happy about that second underscore. All right. Instead of just saying lambda max, I'm just going to say lambda 1. With the understanding that, of course, this corresponds to the wavelength at which the peak occurs for the spectrum of these two stars. And this should fix it. Let's see. All right. So lambda, the ratio of the wavelengths of the two stars is equal to the ratio of their temperatures. Except, of course, you get this whole inversely proportional situation going on between the wavelength and the temperatures. All right. And so I believe that we're given this information as well, right? We're given what lambda 1 is and we're given what lambda 2 is. So the temperature ratios have to be equal to, and I'm going to scroll up so I can be able to find what lambda 1 and what lambda 2 is. Lambda 1 is 500, lambda 2 is 700. So, and they're in units of nanometers. So we're going to get another fraction. Lambda 1 was 500 nanometers. Lambda 2 was 700 nanometers. We'll keep it in fraction form. And this should end up yielding 5/7. That doesn't look too pretty. I'll worry about prettying it up later, actually, for when I post this somewhere. All right. So 500 nanometers divided by 700 nanometers gives us 5/7. So we can actually we have all the information we need to go ahead and solve and the ultimate thing we're solving for is a comparison between their sizes. So I'm going to go ahead and copy and paste that information at the bottom here. But before doing so, let's write out solution for estimate of star sizes, of stars' relative sizes. A relative size. Here we go. So now we can go ahead and copy and paste that. I'm only concerned about the very bottom line, which actually gives the ratio of their size. I'm taking a quick breakdown and quickly look at, see what we got here. Thank you, Susie, for clearing that up. I think you would fit well in with other educational streams. Well, thanks, NJ Vellet. Thanks, guys, for handling the questions while I was doing this. But yeah, I've seen a few of Sky's streams, and I like them. I would definitely say they're probably more so for like an adult audience. But I love her streams though. All right, so now we can go ahead and plug in our ratios, right? So as far as L1 and L2 are concerned, they're given in units of, not units, but they're given in the form of a decimal. So my plan to work with fractions, even though I could turn this into a fraction, I'm just going to go ahead and plug in the physical values that I got here. So L1 over L2, and let's make sure that's L1 over, that is, will end up giving us this 0.091. And let's go ahead and convert 5/7 just to, keep everything in the same sort of formatting. So 5/7 is equal to 0.7, so 3 decimal places. So 0.714. Let's use that. And note that I have to take the reciprocal, no, not the reciprocal, do I? Because it's already T2 over T1. And lambda 1 over lambda, so 5. So I'm perfectly okay to do it like this, actually. So I'm just going to go ahead and put that in there. 0.714. Let's go ahead and typeset that. And so now I can just go ahead and solve for what that equals. And again, you guys can't see me doing the calculation, but trust me, I'm just using my MacBook to do it. So please do trust my solution. But if you don't trust it, which, that's perfectly okay too, just go ahead and verify it by using your own calculator. In fact, I encourage you to to make sure that I'm actually saying things correctly. All right. And so what I'm getting is that this equals, I'm going to round it, it's equal to that. But I do not like the way this looks. I hate dealing with a decimal like this. So what I'm going to do is slightly modify this. Let's see if I do the reciprocal of both the left hand and the right hand side, what do I get? Excuse me. So R2 over R1. So if I take the reciprocal of 0.154, or that is, if I take 1 divided by 0.154, what do I get? So let's keep this. I think I said 1 divided by that. So I get roughly 6.5. That looks a whole lot better to work with as far as numbers are concerned. And so basically, what I'm getting from this is that the radius of star 2 is equal to 6.5 times the radius of star 1. Or another way of putting that is that star 2 is much bigger than star 1. And we were able to get all this information by simply looking at the light coming from the stars, right? We were given the ratio of their apparent brightnesses, and we were given the wavelength at which their spectrums have a maximum. This is all just coming from light. And you can actually do this experiment if you wanted to, that is. You can do it with like light bulbs. Have light bulbs of different sizes at roughly the same distance relative to yourself. And of course, they can have different power ratings, and then you can always just do this test at home if you wanted to. And so that is the first problem for today, which is just basically me picking up last week's problem. I have 30 minutes now, which is perfect. It's probably not perfect enough to get to the entire problem that I have set up for today, but nevertheless, we're going to give it a try. So let's go ahead and start switching up the scene to what we're going to be talking about today. And so let's go ahead and go to my OBS software here. But before doing so, let me go ahead and check some of these some of the comments here, because I get into the state of like just talking and talking and talking about the problem, and then I keep forgetting to actually check the comments. Can I make the font? It sounds like you guys are talking about froglets. Hey, what's going on, Joe, or Big J Tuda? Thanks, Jay. All right, so the next problem will involve a little bit of calculus, but we're going to use online to help us in solving the problem today. And the only reason why I bring this up is because I see someone said that math kills me. Oh, believe you me, Larry, whenever it comes to math, oh, please, I'm so sorry. I probably shouldn't even say calculus, because today's problem is going to be really fun. And let me go ahead and bring it up. So let's go ahead and switch scenes. I think everything's up. So today we're talking about the deflection of light as it passes by a massive object. And this is actually the math. We're going to talk about the math behind gravitational lensing, essentially. That's interesting, Big J, is because I had the same experience. Except I didn't take it sounds like you took more like, true math courses, like for a math major. I had calculus, I had statistics, and then of course, discrete popped up every now and then, and whatever other physics courses I had. What's the math for coming across a roadster in space? Oh man. I'm with you. I'm so with you, Big J. No theoretical math. Well, no math that can't be related to anything physical for me. Oh, so that's what that is. Hey, Adam, welcome to the stream. All right, guys, let's go ahead and jump into the problem now. 1 plus 2 equals 5. I'm pretty sure with given some time, I can show that 1 plus 2 equals 5. Of course, there's going to be an error in there somewhere, but it'll be a fun thing to do. All right, guys. So I'm going to go ahead and I'm going to get rid of all the stuff that I have for, or better yet, I'll just minimize it. So that can go away. This stays. We'll need this. And light deflection will stay as well. All right. And so let me make sure you guys can see everything. Okay. Let's make this bigger. And so one of these days, guys, I'm going to get a tablet and I'm going to be able to write this stuff down, which should make things a lot faster versus me typing it. All right. And so today's problem, and again, I've gotten these problems from my trusty physics book in undergrad. There's the name. It's a very old book. It's been very well used. Slash probably thrown across the room a few times. But hey, it happens. All right. So today's problem, our objective. And note, I quite literally grabbed this problem for today's stream probably 20 minutes before the stream started. So me and you are going to kind of be working through the problem together and or stumbling through it together, which is typically the case for, anybody who's doing these problems, right? Well, not anybody. There are some people who could just do these problems and have no problem whatsoever doing it. But yeah, we're going to see if we can solve this problem. So the problem states, A, use special relativity in Newton's law of gravitation to show that a photon of mass, and it gives m is equal to E divided by c squared, just grazing the sun will be deflected by an angle delta theta given by the equation that we see there, where g is the gravitational constant, r and m are the radius and mass of the sun, and c is the speed of light. And then, of course, finally, B, put in values and show, so that's just basically plug and chug. So A is where all the hard work is at. And note that it says that the photon has mass. Of course, we know that photons do not have mass. However, they do have momentum. And because they have momentum, it's almost the equivalent of them almost having mass. So really, given that equation there, we'd say that m is equal to the energy of the photon divided by c squared. Of course, energy is related to the momentum of a particle, as well as its rest mass. Photons don't have rest mass. So basically, a long story short, you can relate the mass to the momentum of the photon. But honestly, as I was going through this problem in that 20 minutes that I had to kind of prepare for this, I mean, I don't think it's going to be important anyway for our problem. All right. So let me look at comments here and see if there's anyone who has any issues up to this point with what I said. Well, thank you, Big J. And honestly, when I started off too, I mean, it was taking me an hour is a good time to get through some of those problems. Physics 1 problems can be difficult, depending on how far along you are into physics, into the Physics 1 course. Especially when you start getting into doing energy and stuff like that to describe motion. I mean, it can get difficult. All right. So I went online and I found an image of what I think will help us understand this problem. And so the idea is going from the right side of the image to the left. We have some distant star that's emitting light. That light comes in at the initial trajectory that we're seeing on the right-hand side of the sun. However, it grazes the atmosphere, the lower part of the atmosphere of the sun. And upon doing that, sort of interaction with that portion of the sun, the gravitational influence the sun has on the photon, and it's not that it really has a gravitational influence on the photon itself. It's more so the fact that the sun's mass is affecting space-time, which is now going to affect, of course, the photon's travel through that space-time, causing it to undergo this deflection. And so it's going to end up being deflected, and it's going to have a new line now going towards Earth, where now we're able to see this distant object on Earth. Hey Atlantis, I'm gonna shorten that a little bit there. Welcome to today's stream. Thank you for coming by. Oh, so Big J, you can use the kinematic equations of motion to solve that, right? If you assume constant acceleration and you throw away any sort of like non-conservative forces like friction and stuff like that, you can solve that problem. So for this particular problem, we are essentially doing gravitational lensing, and we're talking about the math behind it. All right. So first things first, we need to establish some sort of relationship because the objective is to solve for alpha in our problem. We need to set up an equation for alpha. No, thank you, Neat. Okay, I will not say thank you then. But yeah, I mean, I want to be able to, when we do these streams, we can work through the problem together. And if you guys catch me in an error, please let me know. In fact, I believe in one of my past streams, in fact, with the last stream, I had to make some corrections because of errors. So Peter's stating angle theta is the operative angle for... Oh. I'm going to go ahead and move on to the problem. Is there something else I might have missed? All right. So let's go ahead and establish that an equation for that angle. All right. So what do we know? We know that the speed of a photon is basically c, the speed of light, and it will always maintain that speed. However, due to this deflection, the photon undergoes an acceleration. Not so much that its speed changes in magnitude, but it changes in direction, which causes an acceleration. And so we can actually use that bit of information, that the fact that its initial trajectory is c, and that when it undergoes this acceleration, if we've established some sort of coordinate system where the vertical is y and the horizontal is x, it will have underwent some change in velocity in the y direction. And so I'm using this based off of like how I've set up the problem. And I've written it out. I can actually show you guys. And so at the very top here, hopefully the resolution, it comes through. I've kind of set up like a coordinate system and how I'm seeing the problem in my head. All right. So let's go ahead and let's set up the equation. So no indent. Equation for for deflection angle. And to be very honest, I would have no idea how to do this problem. Well, I would have a lot more difficulty trying to solve this problem if it wasn't for the fact that I've kind of run across a similar, type of problem, but elsewhere in physics. So my background is in high energy astroparticle physics. And there's actually like an analogous problem in the study of ultra high energy cosmic rays that really compares really nicely with this problem. And that is that when you have a charged particle, or aka a cosmic ray, traveling through space, it will encounter not so much gravitational forces, but it'll encounter magnetic fields. And these magnetic fields can cause the cosmic ray, given that it has charge to it, to be deflected. And the math, or the logic behind solving for the deflection angle, is very similar to what we're doing with this problem, just using some different equations. So equation for deflection. Let's go ahead and do that. So what we end up getting is that deflection angle can be determined by using the sine of that angle. So sine alpha. And of course, we need to be able to set this equal to, of course, establish some sort of triangle and set it equal to the opposite side of that triangle over the hypotenuse of the triangle. Well, in this case, we can use the velocity vectors. We know that along the hypotenuse, the velocity vector can be c. So let's go ahead and set up our fraction. So hypotenuse is going to be at the bottom, and its vector, we're going to use the speed of light vector, or the actual trajectory of the particle, or of the photon itself. And for the numerator, we're going to use the y component of the velocity of the particle, or the photon, excuse me. I keep wanting to say particle, but I guess a photon can be considered like a particle as well, but the photon. And we're going to name this as delta y sub v, where this is the y component velocity of our photon. All right. Now, these deflections, of course, aren't going to be very large, especially in the case of like the sun. So, because of the fact that we know they're going to be very small, we can use something known as small angle approximation and actually approximate the alpha, the angle alpha, as just simply the ratio of delta v sub y over c. So I'm just going to copy and paste that. And I'm going to now make it such that we know it's an approximation, so approximate. All right. So far, so good. We are well on our way to solving for what alpha should be. Let me just take a moment to look at... Hey, Black Robe, welcome. Excuse me, 1 times, so 10 to the negative 19 seconds. Where did that come from? I saw a tweet about a Higgs boson particle being created like on 10 to the negative 11 seconds or something like that. Very short time. Yes, that is a very, very short time. Oh, and the correction was 10 to the negative 19 seconds. Wow. You'd have to have some crazy fast electronics to even catch that. Yeah, I don't know much about exactly. I need to read up a lot more on the Higgs boson, actually. Particle. The 17th particle of our now standard model. Yes, exactly. It's insane to think of exactly how fast the electronics have to be. All right, so moving on. Everything looks so good so far, right? So now, of course, alpha is what we're solving for. The speed of light c is a constant. So really, all we have to worry about now is solving for what delta v sub y is. So what is that y component velocity of our photon? And so to get to that, we're going to end up using the fact that we know a relationship between velocity and some other thing that you know the particle, the photon is undergoing, right? It's undergoing an acceleration. And so let's talk a little bit about the acceleration of the particle. No, we did. I mean of the photon. So photon acceleration. And again, guys, as I'm going through this problem, I have my notes and I've like written stuff all over the place. And so I'm kind of trying to choose the correct way in which I want to be able to present this information. So the acceleration of the particle, of course, is, you know what? Before getting into that, no, we can go ahead. We can go ahead and talk about it. The acceleration of the particle is going to be determined by the following formula, at least the acceleration in the y direction. We can state that the acceleration in the y direction for our photon is going to be equal to, and I'm going to square this actually, squared. It's going to be equal to the total acceleration of the particle a squared. Let's actually put a little subscript t, capital T for total, minus the acceleration of the particle in the x direction squared. All right, so far so good. Let's scroll down. So this is what we have for the acceleration, photon acceleration in y direction. In y direction. All right. And so the next question, of course, is, well, what is the acceleration of the photon? Well, this is where Newton's law of gravitation comes into play. Newton's law of gravitation states this. So Newton's law of gravitation. Sorry about that. Begin the line, end the line. And it states the force, and I'll put a capital G for gravity, is equal to the following ratio. Gravitational constant times, in this case, and I'm going to put the mass of m for the mass of the sun, times the mass of our photon, which I'll have a subscript gamma, divided by the distance between the two objects that are gravitationally influencing each other squared. In this case, I'm not going to say r squared, I'm going to say d squared. That's the distance between the two objects. So distance squared. All right. However, we're looking for the acceleration, or we want to be able to make an equation for acceleration. Well, the acceleration, of course, gravitational acceleration, is just going to simply be our gravitational force divided by the mass of the photon. And what you'll easily see now is that the mass, of course, that was given to us in the problem, it drops out of the rest of the equations because of this fact that we're only concerned with the acceleration. And what we end up getting is this. So I'll go ahead and now typeset this. Oops. Let's put those in different lines. And this is what we're going to get from Newton's law of gravitation. That our gravitational acceleration is basically just g times m, where m is the mass of the sun, divided by d squared. And so now we can go back to the photon's acceleration in the y direction, given that we now have... And let me make one more quick note. This is equal to a sub t. Before I move on. So a sub t and this are one and the same. So let's go ahead and copy and paste. I'm going to take a quick break now to look at some of the comments. All right. Thanks, Susie, for verifying that. And so we're going to go ahead and go back to the photon acceleration in the y direction. And we're going to make some substitutions in. So namely, we're going to substitute in for a sub t, of course, what we just found out, which is this. So let's put left, right, I'll scroll down. So far so good. We have a substitution in for that. But now the question is, well, what is going to be the x component of that acceleration? Well, typically you can always do something like the total acceleration times some cosine of some angle, theta. And it just so happens we can do that with this particular problem. Of course, this heavily depends on how you've set up your coordinate system. But I've set mine up so that this works out like this. And we basically can just make the statement that, that we get the following. We'll end up getting essentially the exact same thing. So I'm going to copy and paste that. However, we're going to multiply onto this the equivalent of that cosine theta, which, as I calculated, will end up being your x component, or some distance x traveled by the photon. So some distance x divided by d, and of course capital D, because that's the hypotenuse in our case. And this is going to be squared. So this is the equation we now have for our acceleration in the y direction. And what you'll end up seeing, though, is that, and given our time constraints, I'm going to well, no, I don't want to skip too much. I'm going to do this. We can end up factoring out a gm over d squared quantity squared. So we're going to factor that out. And we're going to be left with you guys are now probably kind of seeing the reason why I want to have a tablet to do some of this stuff. Let's do this. See how this goes. That fraction. I actually should keep all of that. It makes it easier on me. All right, let's do this right there. All right. And so we've gotten to this point. Now, again, we're not at any calculus or anything like that just yet. But we're getting close to getting to calculus. All right, so we now have this. And I'm going to go ahead and simplify the interior of our right term on the right-hand side of the equation to obtain the following. So we'll end up getting a d squared for the denominator. And we essentially get a d squared x squared. We get a d squared minus an x squared up top. D squared minus an x squared. And I think I can get rid of that minus 1. Let's see what this looks like. Make sure it came out correctly. And I can get rid of the square, if I'm not mistaken. This looks like this is going to be one of those problems we're going to have to pick up in next week's stream. But that's perfectly okay. And so we've now gotten to a far more simplified version of we've gotten to a far more simplified version of the problem. And from here we can be able to work out the rest of it, but we're running out of time really quick actually. Okay. And so what we next want to do, of course, and I'm sorry, I'm quickly checking over what I have here. So square root, that's cool. That looks about right. So now what we want to do is we want to take the square root of both sides, right? Because we don't want a sub y squared, we want a sub y. And so I'm going to modify that to be now this. A sub y is now going to be equal to the square root of, and I'll use those. Use parentheses instead of the things I've been using, the brackets. And so we should get this. Oh no, it doesn't like something. Aligned. What did I do? What did I do? What doesn't it like? Okay, there's another way of doing this then. Square root. Everything raised to the 1/2 power. Let's see if this fixes it. Alright, we'll just raise it to the 1/2 power. It's no different than the square root sign. Alright. So, given that we're running out of time here, I'm going to leave it at this. And we're going to definitely pick up this part during our next stream, which is next week. This will give me a little bit of time to go over some of the comments. I really do hope that what I've been saying so far, everyone's been able to somewhat understand or completely understand. That's even better. So, and again, guys, if you have problems you want me to work, send them to me. I'm constantly looking at the weekly Space Hangout Crew's Slack. And so you can post, if you have access to that, you can post them there. But yeah, I think that this is a good place to stop for today, and then resume during the next stream. I'm unsure if. Let me type something really quick. All right, cool. So I'm able to type things. So no one hasn't put anything new since I've just been talking. All right. Well, guys, thank you all for joining today's stream. As usual, it's always been fun being able to talk with you guys about science. And hopefully you guys can be able to join my future streams, which will be next week, Wednesday and Friday, both at 12 Central Time or at noon Central Time. Um, I do know that, well, I believe, thanks, Susie. If I'm not mistaken, there's going to be an astronomy cast today, and that should be in roughly an hour's time. Whatever your time zone may be, the lapse of time is going to be the same. So it should be within an hour, which is going to be 2 o'clock p.m. for me Central Time, 3 o'clock p.m. Eastern Time. And so I'm seeing though in my stream today, I didn't get to any of the calculus, but during next stream there will be some calculus. So I'm looking forward to it a little bit. I hope you guys can look forward to it as well. But thanks for joining, and I will see you guys later. All right, bye.